Good day, everybody. Today we're going to look at Hamilton's method in a little more detail. It's a pretty straightforward method, but we don't use it for certain reasons, and we'll see why. First, all you need is the population of the states. So we've got 2020. You can just get those in PDF or Excel nowadays on the internet, of course, through the Census. So here's the 2020 population, 331 million, the official tally for the 50 states. You can go and get other years too, 2010, 2000, 1990. So for example, for 2000, again, Excel, PDF. In 2000, the population is 281 million. So once we have the population, get it here, I'll just copy the population. So what I've got, 331 million. I'll start here. Oops. Just copy that population. I've got my spreadsheet all ready to take it in. There we go. And boom. Total, of course, it's the same. So we have 435 units to give out, and if you look at the fraction of Alabama's population to the total population, you can just multiply that fraction times 435 to see that Alabama should get 6.61 units, and so on for each state. We call that the standard quota for the state. Another useful way to do it is if you take the 331 million and divide by the 435 seats or units, then you can look at it, well, it's one seat for every 761,000 people is what we want to have ideally. And so if there's 761,000 people per seats, then you can just divide the state's population by that number, the 761,000. And so we would call this the standard divisor, and so we get our standard quota this way. Either way, we're getting these same numbers, the 6.61. So we do that with every state, and of course we can't subdivide people, so we'll have to figure out how to give the 435, taking each state to an integer. So you can just do straight rounding, but most likely you wouldn't reach exactly 435 if you just did rounding. So what we do is we first round down no matter what. So every state got rounded down, even California, that was pretty high, 51.99. So just round every state down. And if we do that, we've given out 410 seats. And now, so we still have 25 seats to give out. If you look at the fractional part that's left over, so subtract the lower quota from the standard quota, and you get this fractional amount. We're not one more decimal point. But we're going to go in order, of course, of biggest fractional part. So we just sort these. Yeah. So we'll sort by that fraction. There we go. And so we can see California should definitely get a seat. So we'll give that a seat, and we'll just keep giving seats until we give out the 25. Just ballpark it here. I got a few more to go. Whoops. Still one more. So there I gave the, well, it turns out in this year straight rounding actually would have worked, but that's generally would not be the case. I mean, it often happens, but you can't expect it to happen. But anyway, biggest fractional parts get the extra seat. So now we've given out 435 seats, and if I just rearrange the seats, the states back to alphabetically, we have our apportionment due to Hamilton. So there's the 435 seats. This column here is how many seats or representatives each state will get. So it's pretty straightforward. We could do it one more time. I don't think we need to see it, but take a quick look here. I've already got the population of this is 2000 with that 281 million, and in this case we gave out 409 seats if you go to the lower quota. So again, it's got a different standard divisor, so population was smaller. So the 435 meant roughly one representative for every 647,000 people. But again, all we need to do is, once you subtract the lower quota from the standard quota, arrange them in order of that fraction. So if we sort by fraction, largest to smallest, and give our seats out this way, see how far I have to go. Perfect. So this year we can see, well, straight rounding wouldn't have worked. We've been pretty close, but so now I've given out the 435 seats, and now I will resort these alphabetically. And that would be our apportionment. So it's not too hard with Excel. Just go once you find the fractional part in order, largest to smallest, give out the seats until you've given out a total of 435, starting from the lower quota. So back to 2020, this would have been it. So this is not used. So why isn't it used? The main reason is there's a few paradoxes that kind of showed themselves as they thought about using Hamilton's method. And one's called the Alabama paradox, or it's also called the House monotonicity condition. And that's if you increase the number of seats, then a state shouldn't have its seat total go down. And what was noticed, they were trying to figure out how many seats to give out, and they did the apportionment for all house sizes between 275 and 350. So they were trying to figure out how many representatives they should have. This would be for the 1880, and they noticed that Alabama got 8 seats if you gave out 299, if that was this house total. And then if you go up 1, Alabama actually went down 1. And here's a little tiny example with simple small values and everything, but population 6, this could be 6 million or 6 million, 2 million. But if you look at the share with 10 seats, and then if you go to 11 seats, you increase the number of seats, but a state lost. A state went from 2 to 1. So this is sort of an extreme example. What had actually happened, or would have happened, they didn't have it happen. So that's one crazy thing about Hamilton. Another is a population paradox and a new states paradox. The new state paradox is if so what happened in 1907, Oklahoma became a state. They'd already done the apportionment, and Oklahoma should get 5 seats. And so this was in 1907. They did the apportionment in 1900. Then they give Oklahoma its 5 seats, but then they just recalculated the apportionment anyway, and they noticed, well, Oklahoma stayed at 5 seats. The total number of seats went from it's right here, 386 to 391, and but New York lost a seat when that happened. So they gave a new state its proper amount of representation, but then in recalculating the apportionment, the other states changed. Namely, New York lost one, Maine gained one. So they didn't like that. And then, of course, the population paradox. And that's when a state gains in population and another state loses in population, but the state that gained in population still loses a seat. So here's an extreme example. You've got these populations here, and give out the 10 seats, and then there's a change in population. So state C gained the most percentage-wise, and it gained 8. State A gained a smaller percentage, and state B lost a significant percentage, but state B didn't lose a seat, state C lost a seat. So that would be the population paradox, that it doesn't necessarily correspond with the population changes like that. So Hamilton's not really used as an apportionment thanks to these. So we will now look at the more popular methods are divisor methods, and they're more interesting. One thing that Hamilton does satisfy and the divisor methods may not, although most of the useful ones will in standard populations, is that each state is going to get either its what's called its lower quota, which we've looked at. You know, that's the least it can get, and the most it can get is its upper quota. So once you figure out how much each state should get proportion-wise, it's either going to get that number rounded up or down, but never any more than that or less than that. But with divisor methods, they might go against that quota or have that quota violation. Anyway, so let's take a look in another video.